In this unit, we describe an important photonic circuit, namely the interferometer. We discuss the basic functionality and discuss some applications. We begin this unit by looking at two common types of interferometers, which can be implemented as photonic circuits on silicon. We then look at the difference between a balanced and imbalanced interferometer. The imbalanced interferometer is the type that is being considered in this course project. Finally, we discuss applications of interferometers, focusing on optical communications applications. Not discussed here, there are also applications for interferometers for spectroscopy and for biosensors. Let's discuss two types of interferometers. The first is known as the Mogg-Zehnder interferometer, or MZI. It consists of two beam splitters where the light is split into two paths. One of the paths has a sample which introduces a phase shift. Depending on the optical phase shift due to the sample in one of the optical paths, at output 1 we will see either constructive or destructive interference, or something in between. The complement will be observed at output 2. Another interferometer configuration is known as the Michelson interferometer. The first difference with the Mogg-Zehnder is that the light travels through the same path twice, hence is twice as efficient at converting the phase shift into a measurable signal at the output. The second difference is that there's only one output. Where is the second output, and what happens if we have destructive interference at the output? The light must go somewhere. The answer is that the light goes back to the input port. Let's discuss the MZI configuration implemented using optical waveguides. We use Y branches instead of beam splitters, and use waveguides that act as optical phase shifters. When the waveguides have the same phase, we see constructive interference. Ideally, the light output is equal to the input light. When the waveguides have a relative pi phase shift between them, we see destructive interference at the output. Ideally, there is no light at the output. This configuration is known as a balanced interferometer. There are two paths that have equal lengths. This device thus operates over a broad range of wavelengths. However, it requires circuitry to bias the phase shifters at the correct operating point. Particularly for experimentation during device development, it is common to introduce an imbalance between the two arms of the interferometer. As we will see from the equations later, this configuration gives sinusoidal oscillations as a function of the laser wavelength. This is useful to determine the performance of the interferometer, for example, to determine the phase shifter efficiency. Also, we can use the laser wavelength instead of the electrical bias to determine the operating point of the interferometer. Using the balanced MZI configuration, we can construct an optical switch. In this example, the device is used to route the input light either to output port number 1 or to output port number 2. Where the light goes is dependent on the phase difference between the two waveguides. The phase shift is introduced by heating one of the waveguides, which slightly changes the index of refraction via the thermo-optic effect. Hence, this subcircuit is known as a thermo-optic switch. The fabrication of this optical switch begins with the waveguides, which are defined using electron beam lithography. Additional steps are performed to deposit a metal heater above the waveguide. This heater is used to create a phase shift in the left arm of the interferometer. Furthermore, the waveguide is under-etched to provide thermal isolation. This improves the efficiency of the device. The performance of the optical switch can be analyzed by plotting the output power at each of the ports on the y-axis versus the electrical power dissipated in the metal heater on the x-axis. At an optical power of approximately 300 microwatts, we see all the light going to output port number 2 and almost no light at port 1. Increasing the power by 540 microwatts, we see that the operation switches. In this case, all the light is at port 1. These two power levels are the two operating points that determine whether the light is routed to port 1 or to port 2. Another important parameter for the switch is the extinction ratio, namely the ratio between one output port and the other at each operating point. We want this ratio to be as high as possible, especially when a large number of switches are cascaded to make a large switch matrix. Next, we discuss circuits that can be built using several of these thermo-optic switches. First, the thermo-optic switch can be built using directional couplers. The directional coupler, in the ideal case, acts as a 50-50 beam splitter and has 2 inputs and 2 outputs. This configuration is more versatile in that it allows one of the 2 inputs to be switched to one of the 2 outputs. Now, imagine we have 2 independent signals that we would like to route separately to the 2 outputs. We can build such a switch, known as a 2x2 switch, using 4 thermo-optic switches. The switch can route input 1 to output 1 and input 2 to output 2. This is called the bar state. By applying appropriate phase shifts, we can operate the switch in the cross state, where input 1 is crossed to output 2 and input 2 is crossed to output 1. One research and development question is how to combine these components into even larger circuits and switch matrices for routing optical data across chips and in communication networks. Here's an example of a 4x4 optical switch. It uses a similar primitive, namely a Mach-Zehnder interferometer switch. There are 16 of these arranged in a non-blocking configuration, whereby there can be 4 inputs simultaneously being routed to the 4 outputs in any order. In the previous example, we looked at thermo-optic phase shifters. Another type of phase shifter is based on a PN diode inside an optical waveguide. The reverse bias voltage on the diode creates a depletion region. This region changes in size as a function of the voltage. The change in the number of carriers, namely electrons and holes, introduces a small change in the index of refraction. This effect is called plasma dispersion, and it leads to an optical phase shift. This effect is very fast, hence the PN junction is commonly used to construct a high-speed modulator by placing it inside an interferometer. Here is an example of a modulator constructed using a Mach-Zehnder interferometer. The 2 waveguides in the interferometer each have a PN junction. Electrical signals are applied to each junction. By applying opposite voltages, we can create opposite phase shifts in the 2 waveguides. Ultimately, the objective is to achieve a pi phase shift between the 2 waveguides. If continuous laser light is provided as an input and a modulation signal is provided electrically, we can obtain optical pulses which represent the 1s and the 0s of the data stream. This device achieved 50 gigabits per second operation. Notice that the device layout includes an extra loop in the top waveguide. This results in a periodic wavelength variation. As the voltage is changed, the spectrum of the interferometer shifts. This is used to extract the phase shift versus voltage. Also notice that the interferometer phase shifters are very long, namely 4 millimeters. This is required because the plasma dispersion effect is weak, hence a long interaction length is required. This requires the microwave signal to travel in a microwave waveguide alongside the optical waveguide. Hence, this is called a traveling wave modulator. For the highest efficiency, the optical and the electrical signals propagate together in the same direction and at the same velocity. This is known as velocity matching. Overall, this modulator is called a velocity-matched, traveling wave, Mach-Zehnder modulator. Another way to build a modulator is to use a Michelson interferometer configuration. The light is split in 2 using an adiabatic splitter. At the end of each waveguide is a mirror, implemented as a loop. The advantage of this structure is that light passes through the waveguide phase shifters twice, hence is potentially 2 times more efficient as compared to the MZI structure. The disadvantage is that this structure does not take advantage of the traveling wave electrodes, hence the phase shifter has to be short. Thus, it has a higher drive voltage. With these pros and cons, this modulator achieved up to 40 gigabits per second operation in a very compact design.